In this video, we are going to make a large multiplexer, and to do it, we are going to use something called a procedural block. Up until now, we used the assign keyword to assign signals to other signals or ports. This is a structural way of describing part of our circuit. However, we can also describe portions of the circuit in a behavioral way, where we describe the behavior of the circuit rather than more explicitly describing the gates that connect them together. To demonstrate how we do this, we will look at a larger multiplex example, where we have 8 inputs rather than 2. The inputs and outputs of our circuit will be 16 bits. We use this shorthand in diagrams to represent this. This is the same as declaring our signal as 15 down to 1, 15:0. Since we have 8 inputs into our mux, we need the select signal to be wide enough to be able to uniquely identify each input. So we have 8 inputs, which means in this case we'll need 3 bits to do this. We can also notice that input 7 on the multiplexer looks a little different. This is a literal, a constant value. We'll learn a little later on, in video 2 of this lesson, how to define them. In the lesson directory, if we open up always_mux.sv, we will see the following stub for our module. We can see the 7 16-bit input ports, the 3-bit select input, and the 16-bit output port. To describe a block of code behaviorally, we use something called an always block. These come in different flavors, but for now we will focus on the always_comb block. Always combinatorial is what that means. In these behavioral blocks, we can write hardware code that looks closer to what we would write in software. We can use if statements, case statements, even loops, although they behave a little differently in hardware. We'll get onto that later. To create one of these blocks, write always_comb, begin, then end. Our behavioral description of our block of hardware goes between the begin and the end. Let's do something simple to start. Let's assign the output port Q to the input port A. So we can write in the body of our always block, Q equals A, and then a semicolon. This will have the same functionality as writing assign Q equals A outside of our always block, but notice that in the always block we do not require the assign keyword. Let's compile this and see it on the waveform. Yep, Q and A have the same value. Great. In such procedural blocks, we can also assign to the same signal multiple times. Remember in a previous video I said that only one bit of logic was allowed to drive a signal at a time. Well, in this case, this is allowed. We can make multiple assignments here because we consider each of these blocks as a single driver. Essentially, each line of code in the block is executed sequentially, and the last assignment is the one that is applied to the signal. So there really is only a single driver. This is different to the assign keyword, where each line would be executed at the same time. Let's demonstrate this by adding an extra assignment in our always block, Q equals B. Make and run the simulation, and then let's look at the waveform. We can see now that Q is equal to the value B, as it was the last assignment to happen in the always block. We can also use internal signals in always blocks. Let's create a 16-bit signal temp. Assign it A, and then assign Q temp. Make and simulate again. And in the waveform, we can see that Q is instantaneously assigned the value of temp. Finally, just to re-emphasize the point, for the purposes of this course, there can only be one driver of a signal. So we should avoid having more than one always block driving the same signal. Remember, we can assign it multiple times within an always block, but we can only have one always block driving it. Well, that's the end of the first video for this lesson. There are 2 more to go. In the next one we will look at literals in Verilog and then build up to our final, bigger multiplexer example using case statements.